Okay, so welcome to this morning session. It's my pleasure to introduce the two speakers that we have this morning, Sebastian Riedel and Pasquale Minervini. And Sebastian is a researcher at Facebook AI Research and also a reader at the University College London, where Pasquale is a research associate. And they will talk about their work in machine reading and reasoning, so at the intersection of machine learning and NLP and symbolic AI. So thank you so much.
Thanks so much. Thanks so much for having me. You might have noticed that this is not quite a title that you signed up for, and there will actually be a lot of differentiable interpreters as well. Closer to the mic? Okay. So this is not quite what you signed up for. It is still because we're going to talk extensively about differentiable interpreters as well, but in the second part of this lecture. The addition is that we're also going to talk more about machine reading, partly because it's hard to fill up 3 hours with differentiable programmers, and also because this will ground things a bit more in applications, which is something that I like. So this is work with Pasquale, who's going to present later on, and also work with Dirk Weissenborn, who's not mentioned on the slide, who's been helping us with building this slide, as well as Johannes Welbel, who is a student at UCL. Okay, so let me get started. On a high level, what this tutorial is about is machine reading and reasoning. And I guess there are two views or schools to that. One is what I call the old school view, which goes something like this. You have some text, and you have a machine that reads this text, and this machine turns the text into some kind of symbolic representation of this meaning, of the meaning of that text. And often that symbolic representation is a graph of some sort. It's relational, so this is well placed within, I guess, the scope of this workshop in summer school. So once you have this meaning representation, you can do reasoning on top of that, and that essentially just means, say, taking the graph, and in this case, looking at drug-drug connections in this graph, and then maybe figuring out that there is a direct drug-drug interaction. And this is what I mean by reasoning. There's things that we perceive, maybe in text, maybe in visual data, and we represent this in one step, and in the reasoning step, we take that and make new inferences of things that we haven't actually seen in the perceptions that we taken in. So that's the old school view, and this has been, I guess, the common paradigm in NLP for I guess decades. There is a new school view to this, which you can remember, which you can imagine has a lot to do with neural networks. And in that view, okay, before I get there, this is essentially the part I'm going to talk about in this tutorial. I will specifically talk about how to go from text to these symbolic representations. I will also talk about how you go from text to essentially non-symbolic representations of meaning, namely vector representations of meaning, which are then used end-to-end, in a sense, to fulfill some kind of downstream information needs. And I'll talk a lot about that. Due to this paradigm shift that we've seen in NLP, and this move from mapping things to a symbolic representation, which we then use for all kinds of things, to mapping things just to vectors, this had to, or forces us to rethink a lot what reasoning means, and what reasoning means in this particular framework where your text isn't mapped to symbolic structures but to vectors. And hence there has been a lot of work in differentiable programming, and in a way that's what I think of as the interaction or the intersection between meaning and inferring new knowledge. And this is what Pasquale will talk about. But I'm going to talk about, I guess, the first half of this picture, whereas Pasquale is going to talk about the second half. All right, just to give you a high-level overview, there's the machine reading part, and there's the differentiable interpreters part. And I'm going to talk about these different ways of representing knowledge, and then address some open problems. Pasquale is going to talk about learning with external memory, differentiable abstract machines, neural theme problems, and then, neural theorem proving, and then also some open problems. Okay, so let's talk about machine reading. I don't know if people have seen this message or this news a couple of months ago, I think in the beginning of this year. There was research done in Microsoft and in Baidu on getting machines to now read better than humans, putting millions of jobs at risk, which is what I guess the news made of that. Obviously, it's not quite like that, not at all, and you don't have to worry. In fact, I think the truth is more like this. Robots can now pattern match on a benchmark data set better than humans. That is certainly true. And it's quite an achievement, and I'll talk about that achievement, but it's obviously by no means like real reading in the way that we understand it yet, and I hope to give you a sense of that. That being said, I think there has been quite amazing progress in what is called machine reading, and the activity in this space is really skyrocketed. So if you look at, say, if you look at conferences in NLP and you look at the different areas and where people submit papers to, this, like together with question answering and information extraction, which is all sort of the same thing in a way, they get the most submissions. There's the most activity there. Still above machine translation, actually. So there's a lot of excitement in this area, and I think it's a good time to talk about it. Okay. So what is machine reading? Well, what do I mean by this? There's actually a shifting, I think, interpretation of that term if you look at the sort of last 30 years. If you look at the time before 2006, and if you Google for machine reading, what you find are essentially machines, literal machines like this thing here, that read things in the sort of real world like a license plate. And then reading that just means mapping it to the actual character of symbols on that license plate. So that's not quite what we do today. From about 2006 to 2014, the meaning of machine reading meant something else, namely this idea of going from text to symbolic representation that I already mentioned earlier. So what you see here is actually an image that comes from the official DARPA machine reading project that happened during this time, that funded a long list of researchers in the area to do this task. And this logo is actually quite interesting, because if you look closer, what this robot does, it's not just reading, it's actually also writing, and it's writing something quite particular, namely a sort of logical form of some sort, or some kind of representation of what the text means. And that was the main interpretation of how of machine reading at the time. Then, I guess, with the advent of neural networks and deep learning, I guess the second advent of it within the context of natural language processing, there was another interpretation of this term. And in this term, you primarily look at what people call end-to-end question answering. So I give you a question, I give you some kind of background text, you map that through some kind of deep neural network, and then get an answer to it, which is, in a way, like dramatically rethinking the way that sort of machine reading was done before, where you always map to this symbolic representation. Instead of doing that, you just feed everything end-to-end through a neural network, including the question, and just care about the answers. You don't care about the intermediate representations anymore. Sorry, that's the wrong slide. So what this first part of the tutorial is about is essentially these two things. And in particular, what I'm trying to give you is a context. What is machine reading? Why should we care about it? The methods that we use for machine reading, the different paradigms, and I already mentioned some, the models that we have been using, and what are the challenges in machine reading? Like, why is it hard? What are the strengths and weaknesses of current models? And what are the tools that people use for it? And in particular, what are the data sets that people use for it? Because really, with this paradigm shift from symbolic representations to end-to-end question answering, a lot of what our day-to-day job is in NLP right now is to build new data sets for deep models, which is exciting to some extent, but it's just the way it is. All right. And this will be the first part, like traditional machine reading. This will be the second part. All right, so just to remind you, I have text. I have a machine that converts it into some kind of symbolic representation, which is then used to fulfill some kind of information need. This will be the general, I guess, pattern of this talk, and these will be the ingredients that I'll focus on mostly. Within this sort of box of how to map text to representations, there's a lot of machine learning you have to do. And so there's obviously deep learning, there's a lot of relational learning, there's unsupervised learning, multitask learning, all of that are ingredients of this task. So if you're interested in any of these things and you're looking for topics, that is certainly a topic you should consider. Why do we need machine reading? I think there are two high-level reasons I always like to bring up. One is the traditional information overload motivation. That is, like if you look, for example, at the number of papers that are published in PubMed, which is a big repository of medical papers, then there's an exponential growth in that over the last couple of years. So it just keeps on getting more and more, and nobody can actually still read all of this, or obviously not all of this, but even the things that are relevant for you, you cannot all read. So if we had machines that could go out and read it for you and then be able to answer the questions that you have directly for you instead of you having to read all of that, then that would certainly be really useful for you. And I think that's one of the core drivers of this field. There's the other motivation for it, and that motivation is essentially part of AI. So if you look at AI and the core challenges in AI, one of them is the so-called knowledge bottleneck, where we've always been able to, for small domains, configure machines and give them enough rules to do all the things we want. But like the minute we make the domain broader, we just cannot feed the machine with all the knowledge it needs manually. This is just too much work. It's too tedious. It's error prone. So what if a machine could go and read up about the topic that it's supposed to solve? Then this knowledge bottleneck might be addressable much more effectively. So I think these are the two things. Like A, it helps us. B, it helps AI to, I think, really reach its full potential. Right, what are applications of machine reading? Is there's question answering generally, and I think this is one of the core applications of it. Like you have a natural language question, you have some text, can you give me the answer to that natural language question? There is helping agents to learn faster. So for example, there's been work by Branavan et al. In 2012, where they used a Wikipedia manual, or sort of background, a civilization manual, maybe taken from some kind of Wikipedia page, to help an agent playing Civilization. Because as you can imagine, you can play a game better if you read a bit about it in advance and read about the strategies that you could follow. That's another instance of why machine reading could help you. By the way, if you have any questions, please shoot right away at any time. This is not yet technically deep, but hopefully later. There is precision medicine. So there are quite a lot of people, including Hoi-Fung Poon, who try to look at what is called precision medicine, in particular who try to look at what people do in these molecular tumor boards. So I don't know if you know about these, but these are essentially groups of doctors who sit together and look at a particular, say, cancer case, and then get a sequencing of the genes, and based on those, try to figure out what to do with this patient. And the way they do this is by then having to scan through the literature and find all the relevant, documents or papers about these specific genes. And obviously, that doesn't really scale very well. So if we can help these boards, and generally the doctors, to do some of the reading for them, then that should make this job much easier. There's work, and I'm quite interested in that, in misinformation and dealing with, I guess, for example, contradictions in the news field, on misinformation or fake news. So, I don't know how many of you live in the UK, but like if you do, then you certainly know about this statement that Boris Johnson made at some point about how much money the UK spends every month weak to the EU, and obviously that was one main driver for why they decided how they decided. That number was quite off. It wasn't like completely off, but it was just a wrong number. And so if we can get machines to read all of this and find contradictions in there and then point us to those, that hopefully helps us a bit with, I guess, the online discourse and a lot of other problems we have in that space. So that's like just a small subset of the applications you can have in machine reading, and people work on all of these. What are different approaches? So this is sort of what you can do with this box. What are different meaning representations and different approaches to machine reasoning, reading? One approach is what's called semantic parsing, and this is really the task of usually going from a sentence, maybe a few sentences, to a logical form that represents the meaning of that sentence. So this could be a first order logic formulation, it could be some other kind of formalism. In any case, it's a relatively precise and well-defined structure, and then there's some kind of model that takes the text and maps it into that. There's something called automatic knowledge-based construction, which is something that I work quite a bit on, and a few other people. And here the idea is to go from usually not just a single text, but from a collection of texts to a so-called knowledge graph, in which you essentially have entities like Tesla and Prague, and you have relations between them like Tesla moved to Prague, which come from the background text that you read. Big players in the industry use these kind of graphs and the construction methods. So, for example, on Google, if you search and you ask an actual question, then often these questions are answered with what is called the Google Knowledge Graph, which is a massive graph of entities and relations that looks something like that. So building such graphs is one instance of machine reading. And then there is what I mentioned earlier, this idea of end-to-end machine reading or machine comprehension, where instead of having some kind of intermediate representation here, you simply just have a neural net there, which gets fed with the text and the information need, usually some kind of question. One thing I like to point out is that, and this is really crucial, that there's this edge here between the question or the information need and the neural network. And that's really crucial because it shows this sort of dramatic difference between the symbolic approaches that people have done before and what people now do in end-to-end question answering. Because what this means is that the intermediate latent representation here in these vectors, so this is going to be my representation for vectors throughout the talk, just to make sure we're on the same page. So the intermediate representation in this vector is not universal. It's not something that represents the meaning of this text in all possible contexts in the way that a knowledge graph to some extent does it. It's something that is very specific to the question. So really, it is not just going from from sort of symbolic representations to neural networks. It's going from universal representations to, in this case, question-dependent representations. And you could say maybe there is like a universal representation here at least, because this part of the network isn't yet fed by the question representation. But it turns out that in practice, in many cases, neural networks get this information from the question very, very early on. So there's really no real sense of a universal representation anywhere throughout this representation, throughout this neural network. Before I go into the details of what we actually do and how we do this and how we represent things, I wanted to just lay out what the kind of things are that we need from these representations. And there, I think in language, 3 fundamental things. One is resolving ambiguity. We want that representation to somehow deal with the fact that the same word in different contexts can mean different things. So we can't just map every mention of the word bank to the same representation, because sometimes it's an actual bank you sit on, and sometimes it's a bank you put money in. The other thing is that we need to unify variation. Like when people express their thoughts, they have very different ways of expressing roughly the same thing. And when you build a representation, ideally you want to unify these kind of variations and put them into a single representation that is easy to search over. So unify variation is a big thing. And then finally, we need to be able to integrate distributed information. We're not just going to look at one text or one sentence. We're going to look at several sentences, and we need to link things together. And that will be another aspect of this. All right, so with this in mind, let's look at how automatic knowledge-based construction does that. Just to remind you, it's the task of going from language to a knowledge graph of this sort. I'm going to use this running example here, this sentence, for most of my part of the lecture, so it's worthwhile to sort of go through this a little. So there are two of Tesla's uncles that put together enough money to help him leave Gospage for Prague. Very simple sentence. We're going to map this to some kind of graph. And ideally, what we want to do with that graph is then answer questions like, what city did Tesla move to in 1880? All right, so what we're going to do is we're going to map this input x to a representation y, and we're going to look at this function r, the reading function that does that. The first step of that function is what people call entity extraction, and I would say entity typing or entity labeling. And usually this is done using sequence labeling tasks. Who knows sequence labeling? Linear chain, conditional random fields? Anybody? Okay, some. Okay, so I try to make as few assumptions as I can. So sequence labeling generally is the idea of taking a sequence of symbols and labeling each symbol with something. In this particular case, we're going to take this document and the symbols in it, namely the words, and label them using labels such as person and location. And we do this because the first thing we need to do is produce the nodes or entities of our graph. And in order to do this, we do have to find them in the text. So this is the first step, sequence labeling using for named entity typing. All right, so in particular, we're going to label 2of as nothing or not an entity. We're going to label Tesla as a person. We're going to label uncles put together enough money to help, again, as nothing. And then Gospage and Prague as locations. So that's the high-level goal of sequence labeling. And that's a task that doesn't just appear for named entity recognition. It appears actually for a lot of tasks within NLP and outside of it. So knowing about sequence labeling is certainly something that you find useful for a lot of things. How is this done? I'm trying to give you a high-level sense of it. It is often, or has been done in the past, using what is called linear chain conditional random fields, which are Markov networks of a particular simple structure that makes inference and training in these models easy. All right, that's my alarm. You know when I usually wake up. I mean, to be fair, it would be 8:30 in the UK, so it's not 9:30, but yeah, it's still a little later. All right, so oh, well, never mind. All right, so there's the linear chain, and that's a common way. There is today something that's called the bidirectional RNN, which is simply a recurrent neural network that sort of works in both directions and uses information from both the left and the right side to label a particular token. And then there is something called hybrid RNNs and CRFs. And I'm going to talk a bit about this here because I think it's interesting, and it's actually a good way of how the old and the new have been combined in this field. So linear chain CRFs are kind of old school. Like bidirectional RNNs is sort of the new kid on the block. That's what people do today. We actually found good ways to combine these two things, and I'm always happy to see that. So let me give you a sense of how this works, and let me give you a sense of how this works in addressing the problem of ambiguity. So one of the challenges, as I mentioned, is that words might have different meanings in different contexts. And Tesla is such an example because it could mean either the person or it could be the brand, the car brand. And without looking at the context, we don't know which one it is. And hence it's hard for us to label this token as a person or a brand. The way we go about this is first by modeling it using, first principles and a graphical model. If you don't know graphical models, it's not a problem. I'll try and give you a very high-level sense of it. Although I'm sure that there were actually people who talked about graphical models in the previous lectures, so I'm not going to talk too much about it. So here we have essentially these circles, which are variables representing, in this case, the labels that we give to the individual tokens here on the bottom. And these are random variables. Then we have a conditional probability distribution that we try to define, namely P of y given x. And this P of y given x is factorizing into a product of what is called potentials, of small functions that look at pairs or triples of these variables and measure how well they are compatible to each other. So for example, I could look at, these potentials are actually so-called local potentials. They look at a single variable here. So these black boxes correspond to terms in this probability distribution. And they say, oh, I like an O for this label, and I don't like a P for this label. They only look at a single label, and they essentially reward or discourage certain labels for this particular token. And then you have the so-called pairwise potentials that look at pairs of labels and see how compatible they are. For example, if you had a P directly following an L, like a person directly following a location, that's usually not so common. And the potentials, the pairwise potentials, they capture this. So in a way, that's a simple conditional Markov random field. And that's essentially standard linear chain CRFs. It's a linear chain CRF because it's a chain. It's a first order chain because there's only a direct connection between these labels and not between the label and the previous neighbor. And that already works quite well, but it isn't so good at looking at the full context of a specific token. And that's why people combined it with recurrent neural networks. And they did this in the following way. They look at these local potentials, the things that score for a specific token. How much do I like it to be a person? How much do I like it to be a location? And when they calculate these scores, they do this based on an RNN. And this RNN sort of takes vector representations that we have for the future, namely the tokens that appear after this, say the fact that there are uncles involved, which should give you a good sense that maybe you're talking about a person here and not about a brand. And they look at the past as well, in this case the left side, and use vectors or vector representations of the tokens there to feed the actual potential that says, do I like this to be a person or not? These vectors themselves, they're produced by essentially word vectors, and I'm going to talk about these in length later on, that represent the words outside of their context, and the previous labels from the specific words next to them. So if I produce the vector for P, I'm going to take this vector, which I produced by looking at this vector, which I produced by looking at this vector, which I produced by looking at this word vector here as well. Yeah? Say again? It is definitely related, and in fact, when you do inference in this model, you just use forward and backward, the forward-backward algorithm. It's not Baum-Welch in the sense that it's trained on actually supervised labels, so it's not latent in that way. But yes, it's definitely, yeah, for sure. And then you do this for everything, and that's your recurrent neural network linear chain. And this currently is the state of the art in this field. It's quite a beast, but it's nice because it combines like old and new in a good way. I mentioned that briefly. Usually when we train these models, at training time, we have the actual token labels that we need, and we just do supervised training, vanilla, say a cross entropy loss on the labels. I say this here because later on I'll change this up a bit and look at different forms of supervision, so it's worthwhile keeping that in mind. All right, so once we have labeled these nodes, we can go back to the original goal of actually creating a graph. And we use these labels on the nodes, on the tokens, to produce the nodes for it. So if there is a if Tesla is a entity of a person here, then we produce a node for that, a person node, and a location node, and another location node, and so on and so forth. We're also going to keep a link between the actual nodes and where these things are mentioned in text. That will be useful later on. So that's essentially the first step of our pipeline from X to Y, from text to meaning representation. But obviously, we need to do more than that. So the next step in this pipeline is called relation extraction. And as you can imagine by the name, it's about figuring out the edges between these nodes. And the way this is done is by actually looking at the text and by looking at the mentions of these nodes and understanding how these words in the text relate to each other. And if there are patterns in there that correspond to the move to relation, then you're going to predict a relation. And that essentially is another step in this pipeline. So notice that we have sort of produced a Y prime, which was the entities, and now with the entities we do another step, namely the relations. So it's important to take this away. This is a pipeline of steps, and that will be important later on. How is this done in practice? It's usually today using some kind of neural classification model, and it's trained by something called distant supervision, which I'm going to describe in a nutshell now. So usually I need to wake up a couple of times, I guess. All right. So what you have to address in relation extraction is this challenge of variation that I described a couple of times earlier. Namely that there are quite a few ways of expressing the same thing. In this particular case, the sentence could have been, or is, help him leave Gospic for Prague. It could have been him move to Prague. It could have been him settle in Prague. All of these things don't necessarily mean exactly the same thing, but they have very similar meanings. When you do this kind of task of going from the language to a relation, you need to be able to see all of these things as instances of the same type of semantic relation. And that's what relation extraction essentially is about. The way you do this, as I mentioned, is essentially, again, through a graphical model, but a graphical model that is very simple in the sense that there are no direct connections between the labels of different relations that you try to predict. And instead, there are only these local potentials that purely look at the specific instance and try to use the information for this instance and nothing else to make the prediction. And again, when you do this, you have some kind of neural network that does it for you. The details of that aren't really important. You can certainly architecture the hell out of this, and it will help. But on a high level, it's really just a neural network. What's interesting here is that the labels that we have for this task, we usually don't have them on a per mention basis. So it's not like people go out and look at a lot of sentences and say, this sentence has this relation, this sentence has that relation. There's some data like that, but only very little, because this is expensive to do, and you need trained annotators to do this kind of task. And the data, yeah?
But do you have to keep only chunks of text, or can you keep the whole text?
Oh, you can give the whole text, and usually, at least, in order to predict these relations, you at least look at the whole sentence. But that's right. You could also look at the whole document. Usually that doesn't help that much. All right, so, but like the challenge here is that we don't have labels on this sort of per sentence basis or per document basis, but we have labels on a per entity pair level. So there exist a lot of data sets or like knowledge bases such as Wikidata, such as the Google Knowledge Graph, that all contain already existing edges between entities that people have either manually entered there or they have automatically extracted before, but usually human created. And they exist in natural form. You don't have to ask people to create these data sets, they exist. So if you work in biomedicine, for example, there exist data sets of how proteins interact with each other. They exist naturally because people need them. So it's not like you have to go out and create more annotation for that. And a lot of what this field has been about is trying to figure out how to use that data in a way to train these relation extractors. And how this works in practice is that you essentially still consider this somewhere as a graphical model where you have a label here for the entity pair, and you know that the label for the entity pair depends on the labels for dimensions. But at training time, these labels here are latent variables. So you need to do some kind of latent variable training in order to figure that, to train the model. And there are things like the EM algorithm you can use for this. There are a lot of other ways you can do this, but there's a whole, I guess, field that just looks at this problem of like dealing with the latent variables in this graphical model. Yeah. Mincenau has some work on that, which is extremely simple. Like the simplest thing you can do is to just say, you know, if I see the label move to between Tesla and Prague, I'm just going to assume that every time I see Tesla in Prague, they actually are about the move to relationship. And then I just put like a M and M here and an M here. But if that's not about him moving to Prague, but visiting Prague, then you actually get a label error. So this is not usually the best thing to do, and there are all kinds of ways to deal with this, but I'm not going to go into detail. So yeah, that's what I mentioned. Not all mentions express the relation. All right. So once you have these edges between the nodes, you need to collapse some of the nodes. Because as you've seen, we also have a him node here. And this him node is not very useful, right? Because it doesn't tell you anything about anyone specific at this point. And if I wanted to query for where did Tesla move, I couldn't answer this question before I've actually collapsed the him to Tesla in this case. So I guess we need to find the edge between him and Tesla in this case. And when we do this, we have the third step in our pipeline. Like we did entity labeling, we did relation extraction, and condition on that, we do coreference labels. So this thing is going to get like longer and longer here. It's a sequence of steps in this pipeline. The way we do this is through usually also some kind of neural classification and also some kind of latent variable modeling. And to give you a high-level sense of how that works, again, I'm going to use this idea of graphical models. And I'm going to say that for each token, or for each, say, relevant token here, like I have a variable that indicates whether it's essentially coreferent to any of the previous tokens. So there's a variable here that indicates whether they belongs to voters. And there's some kind of local potential there that captures how likely that is using information from the text. For chance, there is a variable here that says, does it belong to they or does it belong to voters? And then likewise for they, there's a variable here that says, does it belong to chance, does it belong to they, does it belong to voters? And you define local potentials over this graph, and then you do inference in there. Inference is actually really hard in this problem because this network looks kind of innocent, but it's much more complex in practice, and that's because there are factors that connect all of these variables due to transitivity constraints. So if you know that they here belongs to they here, and let's say, that if you know that they belongs to voters, and you know that voters belongs to this day, then you know that these two days also have to belong together. So there's a transitivity in the coreference problem that you need to capture through a lot of these connections here. And when you run your traditional inference algorithms on this, like belief propagation, I think you heard about, you will run into a lot of problems in this network structure. So what people have been doing is, I think, quite clever, and the solution I quite like, is to say, let's not model the problem like this. This is the way that we have the data, but let's model the problem in a slightly different way. Namely, they don't ask what are all the links between this word and all the other words that represent the same thing. They only look at what is called like the best antecedent. Like, what is the single word in the past that this word belongs to? So for example, for they, there's only a single word, voters, it belongs to. For chance, there's nothing it belongs to, so there's a 0 here. And for they, there is voters that it belongs to. I'm not saying that they also belongs to they, I just say that they belongs to voters because that's the best antecedent. This problem, if I look at the graphical structure of this, has no dependencies between the variables, and it's extremely simple to do inference in this. And that's what people do because of that. Now, the problem is that my training data at training time is not about these best antecedents, it's about these pairwise links. So you have to do some kind of marginalization at training time to actually train this model efficiently. And that's the only complication here. But I like this as an instance of turning a complex problem into something much simpler by just re-representing the actual original problem. And I think it's worthwhile noting that this notion of a best antecedent actually doesn't really exist. It's something that the model has to make up. Because there is no such direct thing. And if you ask a linguist, they wouldn't give you a direct answer for this. So instead of labeling this, we just ask the model, figure out what the best antecedent is, and then it will do so relatively well. Okay. I think coreference is a fascinating problem, and it's somewhat NLP complete, or maybe AI complete, in the sense that to do it well, in a lot of cases, you actually have to have common sense knowledge. You have to know about the world. I'd just like to give you this one example. So in the case that we've been seeing so far, it's relatively straightforward to make this link. But what if you had these two sentences? The trophy would not fit in the brown suitcase because it was too big, and the trophy would not fit into the brown suitcase because it was too small. In both cases, it actually mean different things, and the only way for you to know this is to know that suitcases are usually things you put things into, and they can be, in this case, they can't be too big in this case. It's the trophy that has to be too big, whereas here it's the suitcase that is too, it would not fit into the brown suitcase because it was too small. In this case, it's the suitcase that is too small. In this case, it's the trophy that is too big. So you need to understand things about the world in order to get this right. There's this so-called vinaigrette challenge that looks at dealing with this problem, and we make very little progress on it. It is interesting, and I'll show you that later when I talk about neural question answering, that some of the models we have, they seem to actually get at this without actually having been trained on this kind of problem. And I think that's quite remarkable. Yeah, so it belongs to trophy here, it belongs to suitcase there, only based on sort of common sense knowledge. All right, so we have linked mentions of entities in the same document. Now we also have to do this across documents. So for example, we need to figure out that this Tesla and this Tesla here, that they not mean the same thing, and they shouldn't be linked together. They're different entities. But that this Tesla and this Tesla, they actually are the same entities, and we need to link them together. And again, the way this is done is using neural classifiers and neural potentials. So like you see a common pattern here. Like a lot of what happens in this pipeline of step is really neuro at this point. It is still a pipeline of symbolic computations in a way. And you do some kind of belief propagation in these networks. And so just to give you a sense of how the graphical models look like in this particular case, you have a variable for Tesla here, indicating that this is this person. And you have a variable here for Gospage, indicating which sort of entity it belongs to. Is it the city Gospage, or is it something else? Is it a person Gospage? And when you predict these labels, like trying to figure out which entity does it belong to, you actually have connections between the mentions in a document that in a way indicate that, if this is about the person Tesla, then it's quite likely that this is about the city Gospage, because we know that there's a connection between these two. And hence there are connections in the graphical model that capture this. And then you have this graphical model and you do your standard sort of inference and training of these graphical models. Nothing specific there. Once you have done, or you found these links between different entities in different documents, you collapse them further, and at this point, you've now gone through 5 steps of processing that produced the final graph. And that, in a nutshell, is knowledge-based construction. It's these steps in one way or another, maybe sometimes ordered slightly differently, but entity linking, entity recognition, relation extraction, coreference, and relation extraction. Can I say this twice? But yeah, it's the steps that you've seen there. Yeah.
How do you deal with the like use case 1890? How do you say information in the graph?
Yeah, so that's a good question. Yeah. So in practice, like this graph would also contain, say, things like when did this happen? So that this wouldn't be just single binary relations, but often it would be ternary relations where you have like one node for the relation and it has like an age or date and it has a subject and it has an object. So you're going to triplefy that in one way or another. But it's a bit easier to talk about, I guess, the pure binary case in this way. But yes, in practice, you would need more information. I'll talk about that in a second, actually, to some extent. So there are a couple of, like, this has been really the bread and butter of a large part of our field for a long time. And it works to some extent, but it also has a couple of shortcomings. I think one of the core shortcomings, and one of the reasons that I've given you this sort of sequence of steps and sort of things condition on one thing, condition on another thing, is that there are a lot of cascading errors in this pipeline. So if I make a mistake on the entity level, on the labeling level, then it's going to be hard for me to recover from that in the relation extraction step, and so on and so forth. So all of these errors, they multiply throughout this whole pipeline. So as you remember, there were these couple of intermediate steps. They all can produce errors, and when there's an error in one, there will be an error in the next one. So that's a problem. It gets even worse, because when I want to answer this particular question, there are even more calculations I need to do. Namely, I need to essentially go from the natural language question to some kind of symbolic representation of that question, which I can then ask to this particular graph. Right? This graph doesn't understand natural language, so I need to specify my query in a sort of graph-based way. And this process to go from that question to this representation, that's another source of error. So I have all of these intermediate steps that can all have errors, and these errors multiply. And this is something that we've been fighting for a long time. We've been fighting with for a long time in automatic knowledge-based construction. Another problem, and this sort of relates to your question, is that when you want to do this, you have to think hard about how you want to represent the meaning of the text in symbolic terms. And you have to come up with a schema. You have to come up with some kind of ontology, some kind of formalization of meaning. And that was kind of fine in the case of this simple binary relation that I had there. But like in practice, it shouldn't just be, did that person move to this city, but when did they move to? and why did they move to it? So, what if you wanted to represent reason and causes in that graph, right? You would have to think even more about, like, what are the types of edges in this graph? Is this the right graph? And you put a couple of people together and you try to agree on this. This is actually really hard. And people spend a lot of time just getting this right. And then you get it right, and then you notice that in practice, that just wasn't enough, and you have to redo it again. So that's a actual real common problem that people have here. That's a major challenge. And then finally, and specifically when you, specifically when you have more complex schemas and more complex ways of representing meaning, it's really expensive and difficult and challenging for people to annotate data like this. Like if you tell them, okay, I'll give you this document, build this graph for me, they'll be like, okay, you need to teach me this for a long time. And then you teach them, and maybe they get it right, but then the next guy does it slightly different, and you get a lot of inter-annotator disagreement between these people. So that also makes it really challenging. So all of these are problems. And in this particular case, for annotation, it turns out that if you give people not the graphs, but the questions and the answers, and you ask them, can you annotate questions, and can you come up with the answers for them, they're quite good at doing that. Here's like a document, come up with some questions and write down the answers. They do that relatively well with a lot of agreement. So people are good in this space in terms of annotating things. They're not very good in this space in terms of annotating things. And so is that all of these problems, in a way, have led people to think about, like, is there some other way of satisfying these information needs, if that's what we care about? And I guess one way is to learn the mapping end to end, like to go from the question and the text directly to the answer. And this is what I'm going to talk about now. I'll give you maybe, so I started. All right, just get started. All right, so I've been talking in the first half of this half about knowledge-based construction, mapping from text to symbolic representations. And as I mentioned, there's been a dramatic paradigm shift, and this shift I'm now going to describe. And this shift's been to end-to-end Q&A. Before I really talk about this, I want to introduce you to one data set, and this has been, I guess, one of the main drivers of our field, for better or worse, and it's called the Stanford Question Answering Dataset, or SQUAD. This data set is essentially of the form that I described earlier in terms of end-to-end question answering. Namely, you're given a question, you're given a text, and you're given a question, and you're given an answer. Or you have to predict the answer, and at training time, you're given that answer to train your model. It's important to point out that here, the answer is always a span of text. So generally, the models have to predict not a generic sequence of strings as the answer, but just a beginning and an end point in that document. So it's a slightly simplified problem compared to general question answering, but it's still question in, text in, answer out. It's a data set of about 100,000 samples of these examples. And because this is remarkable and kind of underlines what I said earlier about how much easier it is for people to annotate questions than to annotate symbolic representations of meaning. This was relatively cheap, I think in the order of maybe 10,000 K or something like this. If you wanted to produce a data set of this size for symbolic representations of meaning, that would be extremely expensive and hard. So one reason why this all works is because annotation is relatively cheap and you can produce data sets of this size. And you kind of need to produce data sets of this size to get the models to work that I'm going to show you later on. And obviously that's a big drawback of everything that people do in this space. Yeah?
$10,000 of the cost of producing
the data set, yeah.
The data set is free to use?
It's free to use, yeah. So I mean, $10,000, I mean, it might sound like a lot, but if you think about the time it takes somebody to think hard about unsupervised learning for a long time, right? Like sometimes this, in a practical scenario, this can be more efficient if you have a cheap way to produce annotations like this. It's really the most widely used benchmark data set, I think, within NLP almost today. It has overtaken some of the other contenders like parsing data sets that people have been using for a long time. Squad is really the thing you have to run things on. And as I mentioned, the task is extractive QA, namely extracting spans of text, not generating QA. There are all kinds of other tasks, generative QA as well, but we're not going to look at this. Okay, so just to give you a sense of, I guess, the variety of data sets in this field, that's not the only data set in end-to-end question answering. There are many, and they just come out like, I don't know, every other week, which is really already a problem in some sense, but it gives you a feeling for how this field is growing and what the current, I guess, paradigm is, which is create data sets and then throw models at it. And what we do in NLP is a lot about creating these data sets. You also see, you probably cannot see, but most of these data sets are actually from 2016 or 17 or 18, so these are all relatively new data sets. So everything from here on happened essentially in the last 2 years or so. And obviously, if you're interested in this field and you want to work on this, like the list is on the slides, and we have all the references for it. And I'm also happy to talk about all of these data sets and how they relate to each other. All right, so how do we do this? Task, generally there is some end-to-end function A that takes the text and the question and produces the answer. And this end-to-end function A is going to be a fully differentiable model. That means you can take a loss function defined on the questions and answers and propagate that loss into the neural model or into the differentiable model, and it will get better and better in terms of actually solving the end-to-end task. And I guess that's the whole appeal of these models in this case. Obviously, the architectures aren't as simple as this thing. They will look more like this, and even that is a high-level abstraction of what the actual model will look like. Within the next couple of minutes, I'm going to go into this, not in super depth, but at least in some kind of detail that gives you a sense of what's actually happening. But I'm going to start with a simpler architecture, the so-called attentive reader. And this will be sort of the, I guess, running example for the next couple of slides. It's a relatively early neural model for machine reading, which isn't used anymore as such, but a lot of the components in it are actually building blocks of today's state-of-the-art model. So it's worthwhile looking at this. Generally, this model and all the models I'll show you later on, they have layers with quite common, I guess, responsibilities. And these layers are shared across these different models. They all have, in one way or another, similar layers. The first layer usually is the input layer. And the input layer is responsible for taking the words and converting them into vectors, which is what the neural models that we need to look at care about. So the first step is taking symbols, tokens, mapping them to vectors. That's the input layer. These word vectors at these points, usually they are context-independent representations of the word. Like, because they haven't yet actually seen the context. They're just a representation of a word, independent of its context. What happens in the next layer is composition. You take representations of these words and the words in the context, and you use these representations to adapt the meaning to represent the context. Because you want to know that in this particular case, precipitation or forms relates to precipitation and not to any kind of other thing that you can do forming with. Once you have done the composition, you have sort of context-sensitive representation of the tokens in it. You get to the so-called sequence interaction layer. And in this layer, you're looking at the representations of the words in the question and the representations of the words in the background text, and you see how they match. And you look at this match and you produce a representation of that match somehow, which is then used in the answer layer to produce the answer. And in this answer layer, usually you just have to predict like the start and the end point, or you have to like choose from a collection of candidate answers. It's not really that important. What's important is that you feed that by essentially a representation of the match of these two texts, the question and the background text. So let's go through these steps one by one and look at the specific layers in a bit more detail. So the input layer is, as I said, in charge of mapping words to vectors. And there's a naive solution to do this, which is to say each word gets a one-hot vector where the hot component corresponds to the index of that word. So essentially, if you had a vocabulary of 100,000 words, then you map them to each word to 100,000 dimensional vectors that have exactly one active component corresponding to that particular word. That's something you can do, and that can work. And then it's something that you actually find in practice as well. However, there's a problem with this, which is that these one-hot vectors, they don't really represent the relation between words. So if you have two words like precipitation and rain, they're obviously quite similar, if not like the same, similar, then the one-hot representation doesn't show you that at all. Because in the one-hot representation, everything is sort of orthogonal to each other. Like they're all just, they have zero dot products, and hence, they all look as different to each other as it can be. And that means your model cannot deal with this problem of variation, for example, that I mentioned earlier when I talked about knowledge-based construction. That's an issue with one-hot representations. That's why there has been a lot of work on finding better representations for words. And this work usually tries to set up vectors in a way that similar words have similar vector representations. So rain and precipitation, they should have similar vectors. Precipitation and mozzarella should have quite different vectors. That's not the case for one-hot vectors. One way to do this is to think a bit about the notion of word similarity and what it means. I guess when you look at that, does anybody know what a wampumuk is? Or can you imagine what it is when you look at it? What kind of thing it is? It's an animal, exactly. It's probably furry. Like, I think you have a sense of what this thing means, even though you've never actually seen that word. You don't know the exact meaning. But the reason you have that is because essentially context and the co-occurrences of words can tell you something about the meaning of that word. In particular, there's something that is called the distributional hypothesis, which says that words that are used and occur in the same context tend to purport similar meanings. This is a well-known phenomenon in language, and you can see it based on this example. If we can learn to represent words using this idea, then we can get representations that much more follow what I mentioned earlier as requirements for them. There's a short version of this hypothesis, which is you shall know a word by the company it keeps. There are several ways to implement this idea in actual methods. One way is by looking at the so-called term document matrix, which has as rows the words that appear in a corpus, and which has as documents the documents that appear in a context. And there's a number here corresponding to how often did that word appear in a particular document. And in this matrix, you can say in a way that each of these words has a vector. And you can say that, or you can hope that words that are quite similar will have similar vectors because they will appear in similar documents. So if you have a document about rain, it might also mention precipitation. If you have a document about mozzarella, it might also mention cheese. And so words that appear together in similar documents might have like similar meanings. So these vectors are actually already better representations of meaning in vector space than the one-hot vector that we mentioned before. But these vectors are still relatively sparse. Like if you have, I don't know, 1 million documents or 1 billion documents, then these vectors will be, billion dimensional, but only have very few active columns. And hence, they will still not be generalizing that well. And computationally, they will also be a bit more tricky to feed into the kind of models that we looking at later downstream. So these things will be somewhat collinear. They will be similar. Dot products will most likely be high for them, but they're still extremely sparse. One way to deal with the sparsity is to approximate a sparse matrix using a low-rank matrix factorization. Namely, you have some kind of matrix U of smaller vectors for each word, some kind of diagonal sigma, and then a matrix V. And you can try and approximate these sparse matrices using the product of these two vectors. And then these vectors here, they correspond to dense representations of these words with roughly the same function. And that's essentially the main idea behind what is called word embeddings. Who has like heard about word embeddings? Anybody? Okay, well, that's quite a few. So word embeddings in general are dense vector representations for words, usually of some kind of low dimensionality. So we're talking about like 300 dimensional vectors, maybe 500 dimensional vectors, not 10,000 dimensional vectors. And they usually capture to some degree word similarity. And they're usually trained on some large corpus, which could either happen through what I showed you earlier, matrix factorization, but it can also happen through other means. I'll talk about that in a second. And I guess one of the most popular examples of this is the famous word2vec tool, which really had a massive impact in our field and is sort of the go-to solution. Whenever you start a machine reading project and you need to think about how to represent your words, feed them into vectors, into your models, word2vec would be like the go-to solution, at least the first thing to try. There are also embedding methods that look at the characters and hence also work for words you haven't even seen before. So when you work with open vocabularies, this is really useful. And just to talk a little bit about word2vec, word2vec in a nutshell is really similar, really simple. It's an algorithm, or it's an algorithm that tries to maximize similarity between co-occurring words and minimize similarity between non-occurring words. So we'll try to maximize the similarity between rain and drop and rain and precipitation, but maximize similarity, so minimize distance, maximize similarity, minimize similarity between rain and mozzarella. And usually similarity here is some function of the dot product between these two vectors, in this case just a sigmoid, but you can choose all kinds of flavors here. And what you want is that in vector space, precipitation and rain are close to each other, mozzarella is somewhat orthogonal to it. And in practice, the way you do this is that you scan through your corpus, and you're going to look at each word in the corpus, let's say rain, and you look at the context of it, and you're going to say, okay, rain, I wanted to have a high dot product with collision, with width, with others, with drops, with all, and ice. And I wanted to have a low dot product with things that aren't in this environment. So you try to use these vectors in a way to predict this word here. And it's worthwhile noticing that this is implicitly related to matrix factorization as well. It's like a different way of doing a matrix factorization calculation. So there's actually some theoretical grounding behind that as well. You might have seen these, like it's kind of interesting when you take these vectors and then project them into 2D using t-SNE, for example. You find that words cluster really nicely, and you get exactly the kind of thing you want to see. For example, there are words here about feeling, and words about travel, and like words about relatives, and all of this. That happens sort of naturally if you throw data at it, and that's precisely what we wanted from it. There's also this famous graph here where you can show that within the vector space there are these odd and interesting relations between words. For example, the capital of a country is often exactly this vector away from the actual country. So, you know, there's a capital of vector in that space. Nobody had trained it that way. And if you sort of add that to your country, you actually get to the city that is the capital of that country. And all of that just happens or naturally emerges through training this on unsupervised data. Okay, so now we know how to represent these input vectors and feed them into the neural network. Let's look at how we compose these vectors to be context sensitive. Because as of now, these vectors don't know anything about, you know, where they are. They're just vectors representing general words out of context. And to understand this, it's worthwhile noticing that language is inherently compositional on several layers. So it starts with words that are made out of characters, and phrases that are made out of words, and clauses that are made out of phrases, and so on and so forth. This compositional structure is seen like throughout language, and when we look at context, we need to take this structure into account. We need to take into account that we're not just looking at single isolated units, we're looking at composed, I guess, expressions of meaning. And when we do compose meaning, or when we do compose the word vectors of individual words, we have to think about what kind of inductive bias do we want to bring into the model. And I'll show you what I mean by that in a couple of slides. But in particular, do we model text sort of sequentially? Do we model it as a tree? Do we model it as a general graph? All of that is something you need to think of when you build models like this. And often this will probably vary between the different levels. Like what you do on a character level will be different to what you do on the word level. And you will need this also to capture long-range dependencies in language. So like a lot of what makes language challenging is the fact that the meaning of a word doesn't just depend on the intermediate surroundings of it, but maybe also on words in previous sentences. And you've seen the example of coreference as an example of where that can actually be the case. All right, so I guess what we want to have in our model in one way or another is the ability to say that, for example, move from Gospic to Prague, that roughly means the same as leave Gospic for Prague. But it's different to leave Prague for Gospic. And you know, if we just look at word vectors, we don't get that behavior. Because if you look at, say, the meaning for Prague, or the word vector for Prague, it's going to be the same here, and it's going to be the same here, and the same here. Like it's the same word vector in all cases. So that's not going to capture the fact that Prague at some point is the target of a move, and sometimes it's the source of a move. None of that is captured in the word vectors. So what we need is essentially some kind of contextual word representation that you know, has a different representation for this Prague than for this Prague, but a similar representation for this Prague and this Prague. And that leads us to, I guess, a general framework for representing word in context. what I'm going to show you now is like a way to go from, I guess, a set of tokens with independent word representations to context-based word representations. There are different options to this. One of the most common ones is the recurrent neural network. We're seeing recurrent neural networks. A few of you. So recurrent neural networks are essentially deep neural networks that process, in this case, sequences, in this case, say left to right, where you have some kind of initial representation, initial vector that you feed the recurrent neural network with, and you have some kind of observation here that you feed the recurrent network with in every state. And the network will take the observation and the previous representation and apply some kind of function to it to produce the representation of the next state. And then that representation is fed into the next step, and so on and so forth. That's essentially a recurrent neural network in a nutshell. And you can see that it's able to, in a way, represent at this vector here, not just what this word is, but essentially everything that happens before as well. And you can do it in both directions. And we did this earlier when I talked about named entity labeling. And then you actually have a context representative or a context-aware representation of your word. So here the idea is generally represent text as sequence. There are all kinds of types of this. I'm not going to talk about this. There's the long short-term memory, and there is the gated recurrent unit. And we have, I think, actually, you mentioned, Arthur mentioned some of these yesterday. So it doesn't really matter what you have here, but they're just different ways of essentially each step calculating the next vector. The bias that we're injecting here is recency. So we believe that the meaning of a word sort of depends on the past, but it mostly depends on your intermediate past. And that's a reasonable assumption for a lot of language. So more recent symbols have bigger impact on the hidden state than the current symbols. There are a lot of advantages to this. What's great about this type of model is that everything is connected. Like even here, you still get a trace of this word in the representation. And that means like in theory, you can capture not just the intermediate context around the word, but everything that happens in the document about it. And that can be quite powerful. And it's relatively easy to train today. Like we have a lot of experience with these models. They come sort of pre-built in your favorite neural network libraries, so that's all good. There are also disadvantages. One, it's relatively slow, and that's primarily because you have to go through these steps sequentially. You can't do them in parallel. And that's a big problem because today's GPUs, they're really good at parallel computation, but there's almost no parallelization here, at least inherent to it. And that makes it slow. You always have to compute the previous state to compute the next state. And even though in theory they can capture long distance dependencies, they're actually not that good at it. Like it's very rare that really the representation of a word here still has a substantial impact from the representation of a word like 20 words before. And that's a problem. They're generally therefore good for sentences and maybe very small paragraphs, but you wouldn't like do them or really use them for long documents necessarily. There are different variants of this, but I'll skip over this. So we have looked at input representations, compositions. Now we're going to look at the interaction between the vectors that come out of these different stages. So we have now in each state composed new vectors that represent the context of the words, not just the isolated meanings of the word. And now we need to see how well do they match to see whether, what the answer to the question is. We need to look at the words with respect to the question that we care about. And the way this is done, or why do we have to do this? Like QA in a way means matching the question in the text, right? You need to somehow find the area in the text that matches the question the best, and then extract from that the answer. And hence you need to do this kind of matching. There is a naive approach to this where you say, oh, I'm just going to concatenate the question and the question and the text, and do my RNN and everything, from that, and then just classify the answer. But that generally doesn't work so well because there are really long-range dependencies between, I guess, the words in the question and the words in the text, that by concatenating them, you're giving the model a really hard time to capture those. And hence, what people do in this space is so-called attention. So attention is one of the, I think there are a few main building blocks in I guess, neural modeling of language. Recurrent neural networks is one, word embeddings is another, attention is the other. And attention works like this. You essentially produce a new representation of a particular word by taking the weighted sum of a sequence of vectors. And the weights of the sum, they depend on how well that particular token, in this case, matches the question representation. So you have a relevance weighted pooling of vectors across a sentence. Like formally, you produce a vector here R as a weighted sum of these attention weights alpha for each possible token here, and the actual YTs that you have there. And what's important is that these alphas here, these attention weights, they are calculated again as neural network representations of the question. And hence, you essentially measure how a question relates to a particular token YT. So when we produce the vector here, that averages, or that the attented vector R, we essentially take all of these vectors here and multiply them with a factor that depends on how well does that word represent or correspond to the representation of the question. And once we have these two representations, we combine them, concatenate them in one way or another, and then predict the answer from that. And just to give you an intuition for how attention works, yeah. Attention is not supervised, so nobody tells you essentially what are the important words that you need to care about. The model will have to learn that for itself. So it's unsupervised attention in all cases. And then if you look at these attention weights, these alpha t's, what they correspond to in a way is relevancy mask. Like for a given question, the attention weights will be such that they will be high around areas that relate to the answer of the question. And that's the intuition behind it. It's like a way for the model to say, oh, I should probably, based on this question, I should probably focus on this area. And then when I calculate the representation of the text, I mostly take the vectors from this area and nothing else when I combine things. Okay. I guess I have 7 more minutes. Okay, so I think that works well because I've given you sort of like a high-level overview of this neural network and the different layers. Pretty much every model has these layers. They're just much more complex in practice. Like they're deeper and deeper, and there are various iterations of these models, but they all have this structure. Just quickly, when you get to the final representation, to the actually, let me skip this because I talked about this already. There are other kinds of composition functions, but instead of going there, I just wanted to quickly, can I go and do the example? I just wanted to give you a sense of how this works in practice.
Okay, so we have to do that. Okay, just okay. Okay.
That works.
Yeah.
What is that? You don't want to use them?
Yeah. Okay.
All right. Okay. So I guess I wanted to do two things. One is to show you some tools you can use for machine reading that I think would be useful for you, and in general NLP tools. And one is called NNLP, done by the Allen Institute for AI in Seattle. They have a range of really interesting and good models and visualizations of it. And one of the models they have is an actual machine comprehension or machine reading model. They have things like textual entainment here as well, semantic role labeling, other things in NLP that if you want to get a sense for it, this is amazing to play around with it. But in the context of this tutorial, I want to mostly talk about machine comprehension. So they have the so-called BiDef model here, which is one of the state-of-the-art models in this field. And I just wanted to play around with this and put some in there. And so I thought I'm going to look at this guy and figure out something about this guy, Christian. So, and I guess he has a homepage here, which is quite nice. And I tried to find his bio papers award. So let's look a bit at his bio and do some machine reading on his bio. So let me take like this part. So like I have obviously tested this one time before. So while I was doing this, what? Famous? Yeah. Yep. I mean, that's what I wanted to say. So one of the things that happened when I was playing around with this is that I thought, okay, maybe this. I was playing around with different length of spans I wanted to copy, and this one was a bit short. So I thought, why don't I take the award section of his bio as well? And then this ended up here, and that was way too long. So I think Christian has too many awards for machine reading, and I only have to take this bit here. So let's copy this and put it in there. And then, so you put some background text in there, and then you can ask a question like, when did he do his PhD? Where's the question mark? Oh, there, okay, yeah. And what it does is it finds the right answer there, and it does that essentially through the steps that I showed you, right? Like it somehow figures out that it should be looking in this area because there's probably the word PhD there. I think you could also ask, just to give you a sense of what I mean by variation, if you ask, when did he graduate? So let's not use the word PhD. It still figures that out. So that's amazing, and be like, oh wow, that's the future. That's really great. So now, just to give you a sense of that it's really not that clever yet. When did Christian fall in love? All right. Is that true? That is true? Say again? Yeah. So for you it was much earlier or later? Oh yeah, well we don't go there. All right. So in a way, it doesn't really matter what I write here. It has learned to match the idea of I guess the when question to dates, which in a way, I mean that might sound silly, but I'm already amazed by that because it has essentially implicitly learned how to find dates, which in the past we have done through annotating dates in text and saying maybe this is a date, right? Or like it also probably it has learned about people. I don't know if I mentioned any people here. No, like in your bio, you never mention other people. You're quite self-centered in that way. But like for example, it figured out like how many So it figured out that as well. So it has implicitly learned to find numbers that aren't dates, right? And link essentially general numbers to how many questions, right? And sort of match that to the neighborhood around it. And I think that's also, that by itself is quite amazing. But by no means are they really better than humans at this point. You cannot say that by any stretch of imagination. But they do something quite useful. And I think that's why I want to leave it now, because I guess it's 10:40. I have a lot of other things to say about other problems of machine reading that I'm happy to talk to you offline about if you want to hear about. There's a lot of work to be done. There's one quick thing I wanted to say, because that will segue into Pasquale's talk. This is that while these things work well, and in a way they work a little better than a lot of the knowledge-based construction stuff that I've shown you in the first part of the talk, what is completely unclear in this framework is how do you do reasoning there? Because in these symbolic graph representations, we could use symbolic reasoning to infer new facts, or we can do link prediction to do new facts, and Matthias will talk about that later on, I think. But when everything is latent and your intermediate representation is just a bunch of vectors that you compose and compose and compose again, it's not clear what it means to do inference and reasoning on top of that. And that's where Pasquale's talk will come in and try and give you a sense of how we're thinking about reasoning in terms of differentiable interpreters. And that will be the second part of the talk. And that will be it. Okay. Bye.